we're looking at a current configuration in which we have these two semicircles of current connected by two straight lines of current to kind of create this little C shape or something. And we want to find the magnetic field at this point P at the center of both of these circles. So we're going to use Biot-Savart's law, dB equals mu naught over 4 pi IDS cross r hat over r squared. And what we need to do is we need to kind of break this into 4 separate pieces. So let's look at the two straight pieces first. For our straight pieces, we get kind of a nice little thing that if we were to look at, right, a little section from here and the vector to P, or a little section from here and the vector to P, right, these being our r vectors, then looking at this, the r vector for each of these is just going to be negative x in the I hat direction. That we either have to go in the positive I hat or negative I hat direction, just depending on what our value of x is. For ds, which is the direction of the current is going in the x direction, positive x direction for both of these, and the distance between this slice and this slice is a small value of x, so we can call that dx. What's really nice about this is that when we do for these straight pieces, right, we are going to have mu naught over 4 pi I dx plus I hat crossed with, well, just r hat would be negative I hat or positive I hat over x squared. Why is this interesting? Why is this cool? Well, I hat crossed with I hat or I hat crossed with negative I hat is 0. So we have no contribution from the straight sections. So we only have to worry about our inner curve and our outer curve sections. So let's look at those. Let's look at our outer curve first. So just as we did for the straight pieces, we have to define r vector ds and then plug it into here. So our r vector for our outer piece, well, using the Cartesian system is going to be really, really tough. So we want to use the RTZ system. So the first thing is that, right, our pieces from the outer are going to look maybe something like this. And our RTZ system is going to be such that we have the r direction in this direction and the t or the theta in this direction, right? Here, r, and theta. And so no matter where I am on this curve, the distance that I have to travel from this curve to the center is always b. And the direction I always have to travel is towards the center. And towards the center is negative r hat. So the reason we use RTZ systems is because when we have curved pieces, our r vectors become very, very easy, right? From this we can find r0 squared is just b squared. From this we can find r hat 0 is going to be just negative capital R hat. For the ds for this, the ds for our outer section, each of these are actually a tiny piece of arc length. If we remember, we have our arc length equation. S is equal to r theta. So then ds, the radius can't change, but how much theta we go through can change. So our ds is going to be r d theta. So the r is going to be b and d theta. And then we have to think of the direction the current is traveling as it's traveling along this. It's going from angle 0 to angle 180. It's going positive. So this would be b d theta plus theta hat. So now that we have this for our outer curve, we can write our dB, mu naught over 4 pi. We have a current I. We have b d theta plus theta hat crossed with our r hat, negative capital R hat, divided by our r squared, b squared. So we can do one quick cancellation before we get too excited about anything else. The b will cancel with the b. And then we think back to another video or another training that we might have had of theta cross r hat. We can also use right-hand rule number 1, where if we curve our fingers with the current, then our thumb points towards me, the person doing the problem, which means it's in the positive z direction. So we get from this mu naught I over 4 pi b d theta in the positive z hat direction. So our next thing to do is to find the magnetic field from this outside, and that's then an integral of naught I over 4 pi b d theta plus z hat. So we need to find the limits. What's the smallest value of theta? What's the largest value of theta? So our smallest value of theta is going to be 0. Our largest value of theta is going to be pi. And so as we look at this, mu naught I, 4 pi, and b don't depend on pi at all. Z hat doesn't depend on theta at all. So we just get a factor of pi from this. So we get mu naught I, we can say pi minus 0 if we want to, over 4 pi b in the positive z hat direction. So I'm going to cancel, right, the pi minus 0, which is also known as pi, and this pi. And that's our answer for the outside. Let's look at the inner curve. We're going to have a lot of stuff be very similar, so we'll hopefully go a little bit faster than that. Our R naught, now we have to travel a distance a from here to here. So our R vector for the inner is going to be a, but we still have to go the same direction, negative r hat. Cool. So that means that, right, our r squared is going to just be a squared. Our r hat is going to be still negative r hat. And then our ds for our inner is going to be now this arc length. So the radius for this arc length is a. And we have still the d theta. And we have to think about which direction the current is traveling. Well, now the current is traveling in the negative direction, so we would have negative theta. Cool. So now we can do our dB for our inner and write it out. Mu naught I a d theta negative theta hat crossed with negative r hat. And we're dividing the mu naught by 4 pi, and we're dividing this section by a squared. So we still get cancellation of the a squared with the a here. And since we had theta hat cross r hat equals positive z hat, negative theta hat cross a negative r hat, right, we just have one extra negative sign, should give us negative z hat. The other way to think of this is, right-hand rule number 1, curving this way, thumb now points at you, the viewer, which is negative z hat. So we get a very similar thing as what we had here, just we have 4 pi a instead of b, and we have positive d theta, and just in the negative z hat direction. So we'll take the integral again, a bit quicker this time because now we know our limits are also going to be, right, smallest angle 0, largest angle pi. We've already determined the direction from this negative theta hat, so we don't have to double count it. 4 pi a d theta negative z hat. And so we're going to get mu naught I over 4a negative z hat. Cool. We did the outer curve. We did the inner curve. What's left? We have the net field. Well, we have our two straight pieces, 0 plus 0. We don't really have to do that, but might as well have some fun with that. We have then our outer piece, mu naught I over 4b in the positive z direction. And then our inner piece, mu naught I over 4a in the negative z direction. And so we get mu naught I over 4 in the positive z direction of 1 over b minus